Having me over. It's been a lovely trip so far, and I look forward to sticking around next week for the meeting. So I'd like to tell you a little bit about work that has its genesis here. In fact, two of my collaborators are from or have connections to TIFR. Suresh was a Sandeep's student, and Kevin was a postdoc here. So Kevin's now at Wits, and this is Kevin's first PhD student, James Messiaen, who is finishing this year, and Suresh is now in Lisbon. So I'll tell you about some work we've been doing lately on non-extremal black holes and trying to see whether they can understand aspects of their physics. So to outline the talk, I'll briefly talk about black hole thermodynamics and statistical physics to provide a bit of context for the ideas that we'll be discussing. And then I'll discuss a curious property of non-extremal black holes. If you take a general non-extremal black hole in 4 dimensions, for example, and you multiply the area of the outer horizon with the area of the inner horizon, this gives the extremal area squared. So this property generalizes to a vast class of black holes, and we'd like to use the attractor mechanism, n equals to supergravity, to motivate this behavior, at least for a certain class of black holes. So that's the main focus of this talk. We'll also say a few words about what the area of the inner horizon might mean entropically. And I'll conclude with giving some prospects for future work. Okay, so this is probably unnecessary in this audience, but string theory is manifestly the correct language for thinking about black holes. And this is clear because we know that the radius of a black hole scales with a Newton coupling. If you take most gravitational systems and you make the Newton coupling stronger, they'll become smaller. For example, planetary orbits will become smaller if you increase the Newton coupling, whereas black holes get larger with G Newton. And this is a test that black holes and black hole microstates in string theory pass. They also become larger as you scale the Newton coupling larger. So it seems that string theory is definitely the correct language for discussing this type of physics. So we've also known since the 70s that black hole thermodynamics gives us a language for discussing black holes in terms of more familiar ordinary thermodynamics. And in particular, there's a first law which relates the mass to the area and the angular momentum and the charge. And there's a temperature and an entropy you associate to the surface gravity and the area respectively. And the generalized second law says that the total entropy, if you take the entropy of the universe into account, the total entropy is a non-decreasing function in time. So this idea of thermodynamics really applies very generally to non-extremal black holes. But as far as understanding what the entropy is counting, we only have an understanding for the extremal solutions in string theory. And a solution is, for which we can understand what the microstates are fairly limited. So it's been proposed that the way to do this thing follows this Strominger-Vafa paradigm. We consider some counting at weak coupling or zero coupling of degenerate supersymmetric vacua, and as we tune the coupling of the theory, we'll go from an open string description in the Higgs branch to a closed string description in the Coulomb branch, and finally we may end up with some fuzzball type geometries that account for the actual entropy of the black hole. This is partially successful in that we can do enumeration in this way from the degenerate vacua to some strongly coupled putative geometries. But the story only really holds in very special, very symmetric cases. And it's not clear how far the story generalizes. One of the lessons we abstract from the story, however, is that quantum effects extend all the way to the horizon, and the horizon scale. And we can see explicitly in the fuzzball geometries. We also see this from other arguments like the firewall, that there may be physics that extends to large scales in gravity. And understanding physics then of these systems requires some deeper understanding of what the microstates really might be. So the two examples for which we have exact constructions of explicit statistical physical microstates for black holes are the D1, D5 system and the half BPS LLM geometries. These are the only two systems, one's quarter BPS, one's half BPS, for which the story holds in that we can associate exact states maybe to the entropy. Even if we have supersymmetry, we include an extra charge, for example, D1, D5P, the 8th BPS systems, we don't construct enough explicit microstates to account for the entropy. And the story is more complicated in ADS5, where the first large black hole with a finite entropy and supergravity is a 16th BPS black hole, for which there, a few months ago, there was a proposal to compute its entropy in terms of an index using something rather like the attractor mechanism. But the actual microstates are completely unknown for the class of black holes that are large. So given this is a situation with supersymmetry and extremality, what happens without supersymmetry and without extremality? Can we say anything at all about these black holes? And I'd like to argue that some aspects of this general picture go through, in that we can, for example, account for the entropy for these non-extremal black holes. And I'd like to use the attractor mechanism to motivate some of the story.
I'm really sorry.
Yeah.
Please excuse me. But just to understand the basic picture, and I don't want to make this into a discussion of fuzzballs or fireballs and so on and distract you, but I mean, I always thought, the back of my mind, that if you want a particular geometry for one of the Bekenstein, e to the Bekenstein worth of states in a black hole, then that'll probably be singular, as in not even admit an understanding in the classical limit. But the average, in a sense, is what the unique black hole solution represents. I mean, your one classical solution at finite temperature, say if you put in spherical symmetry or something, Birkhoff's theorem guarantees that.
Right.
And you have many microstates. And so obviously each of those microstates doesn't correspond to a classical solution.
Sure. So that's right. So
I'm just asking whether that is the general philosophy you're going to.
I'm just going to be mostly thermodynamic rather than physical in this talk. So I really don't have much to say. Some observations, though, are that if you take these LLM geometries, which are non-singular, and you do average them, you do get this singular half BPS superstar. If you take these fuzzball geometries in the D1, D5 system, and you average them, where averaging is a bit, it's not clear how you average different space-time metrics, but if you just accept some limiting prescription, limit shape, some mean field description, you do recover the usual geometries. The difficulty with this kind of picture is that the states in which you expect gravity description are sitting here on the Coulomb branch, maybe, where there's a closed string language for describing the system in gravity. And it's not clear that every state in the Higgs branch has an analog in the Coulomb branch. And in fact, the states in the Coulomb branch here, this matching between Higgs and Coulomb really only happens in D1, D5. So Sen has some general arguments saying that the states up here are zero angular momentum. And these zero angular momentum states are what account for the entropy, whereas the states down here generically have angular momentum. And as a result, you're never going to reproduce the amount of states you need from this. I'm not sure that story is fully settled. There was a paper earlier this month by Mathur and Turton that argued that Sen was a bit wasn't completely careful in addressing singularities and so on in the solutions.
There's some subtlety about Euclidean and Lorentzian here. Because Ashok's argument was based on the partition function. Because it is Euclidean as an Euclidean path integral. Right. There's something happens when you actually think of Lorentzian.
States versus.
So yeah, okay.
Yeah,
So this was just context. It wasn't really something I'm going to say very much about. I'll discuss some non-extremal black holes, and the generic black hole we see in the sky is non-extremal. And these black holes are differentiated from the extremal black holes, and the extremal solutions satisfy some BPS condition. The classic example are Kerr and Reiser-Nordström. And these solutions have an inner horizon. So the inner horizon is in the interior of the black hole, and it shields the singularity. And the entropy is really associated to the outer horizon. But thermodynamic properties can be associated to the inner horizon as well, as we'll see. So the inner horizon is a very peculiar thing in gravity. So if we consider the stability of the inner horizon, even the linear level in gravity, it turns out these things are generically unstable to perturbations. So the idea of even associating thermodynamics to the inner horizon in a really gravitational system with an unstable inner horizon, it may not make any sense. Nevertheless, we'll see what we can say about this. So,
Sorry to interrupt
yeah.
again. For the extremal Reisner Nordstrom, I understand why there's an instability of the inner horizon, going back to the work of
Yeah.
Chandrasekhar Natal, that you have this blue shift, and so on.
Right.
Is there a similar way, just from kinematics, to understand it for the extreme curve, which is sort of more complicated?
No, I don't know of such a sharp explanation. For the Reisner-Nordstrom, as you say, the idea is that there's relativistic counterstreaming between ingoing and outgoing modes, which builds up pressure at the inner horizon. And if there's matter in the theory, this leads to an instability. And this infinite blue shift leads to a phenomenon called mass inflation in literature. I was aware that Penrose and Poisson in Israel looked at this. I'm not aware of the Chandrasekhar references, but on this. Okay.
Yeah, which is just that the infinite history of the universe at ascribed plus or minus past gets projected to finite proper time at the inner horizon, and therefore there's kind of a blue shift and so on.
Right. Okay. I wasn't aware of those references. I was aware of these, but I'll look for those papers. So in any case, the inner horizon is unstable. So I'll think about the inner horizon as really an arena, and really not think about too much about the dynamics in the inner horizon as the story proceeds. Okay, so an observation which was due to Finn, who was here earlier this week, was that if you take the product of the areas, it's a function only of the quantized charges, and it's independent of mass. So I'm going to, for notational reasons, denote the inner and the outer horizons by r plus and r minus. And the areas of the two horizons will be functions of r plus and r minus. And the area of the extremal black hole I'll call AX. And if you take the product of the two areas, you'll find that the extremal black hole's area is a geometric mean of the outer and inner horizons for a family of black holes that correspond to moving away from the zero temperature limit. So this observation by Spadish, Gibbons, and Pope, they found this applied to a wide number of black holes in various dimensions, including Kerr, Newman, Myers, Perry, and so on. So this is the phenomenon which I'll try to use the attractor mechanism to explain.
So there is no GR understanding of this?
It's sort of phenomenological in that it's seen to be true in a wide class of examples. But there's no derivation other than the one I'll present. And that derivation is really specific to n equals 2 supergravity. So it's not a general result in that sense. If you decide to associate entropies to these horizons, if the area and the entropy are proportional, then the implication is that this law implies that equality, that relation.
What's the natural interpretation for S minus?
So there isn't one that I can really propose. There have been some suggestions in the terms of the fuzzballs that if you look in some FP frame for the D1, D5 system, and you notice where the microstates associated to non-extremal fuzzballs, which are a tiny fraction of the microstates needed to describe the entropy, but nevertheless, if you do this, you'll find they vibrate primarily along some interval. So Martinek has proposed that the endpoints of this interval really map back into the gravity story into the inner and outer horizons. And he has some arguments that support this. But again, this is this is not a very general statement. And as well, you expect microstates for extremal black holes also to vibrate. And there you expect it to vibrate over some region. And it's not clear how to go from his non-extremal story to an extremal limit. So I don't know what the entropy really means there. I'll say a few words at the end, but I don't have anything concrete to say.
I mean, anyway, along also the line perhaps what Schmidt was saying, as a zeroth order step, we can probably associate a temperature.
We can associate temperature.
Killing
Yes,
vector
yes,
and-
absolutely.
And then, and you might be coming to this, so please excuse me, but can we formulate the first law of thermodynamics?
Yes, absolutely.
Because that's,
Yeah.
and then one might, then one might be able to relate sort of TdS at the inner horizon to dm, which is
Yeah.
related
Yeah, yeah.
to TdS at the outer horizon, and come up with some GR statement of the
Yeah.
product, which is around.
Looks like a classical
Yes.
Don't even call it T, call it a surface gravity.
Yeah.
But I mean, that's in this.
Yeah.
So there's some curious properties about the temperature. It'll turn out to be negative, and this you can see immediately from this area relation. As you become more non-extremal, the area of the inner horizon becomes smaller. So you associate really that to a negative temperature at the inner horizon. So this implication of area to entropy, it turns out not to hold when the small relation is violated. So if you compute entropy as some no-third charge associated to diffeomorphism invariance and gravity, and you can do that for any horizon really, you'll find that the product of the entropies of the non-extremal system are not the square of the entropy of the extremal system in the case where the small relation is violated. The small relation is essentially a statement about homogeneity of scaling for the various terms that appear in the various charges that appear. So if you have some system like this and you do these rescalings, you can integrate the first law to a statement about M and TS and phi and Q. This is the analog of the Gibbs-Duhem relation, where you use Euler's homogeneous function theorem in statistical mechanics to integrate the first law there. So this homogeneity of scaling is violated, for example, in certain higher derivative theories if you don't include all the higher derivative corrections systematically. So in those cases, it turns out that S plus S minus is not equal to S extremal squared. However, A plus A minus still equals A extremal squared.
But aren't you supposed to replace S by the wall entropy instead of?
Yes, absolutely. When you replace S by when you use the wall entropy in this formula, it turns out this is an inequality when the small relation is violated, but this is still an equality.
When A are now the correct areas with the correct
Yes.
solutions.
Yes.
Oh. So A is no longer just the, I thought S was the corrected wall entropy?
S is the corrected wall entropy. A is just the area.
Yeah, that's what I thought.
Area of the corrected solution.
Yes, is the solution. Yeah, yeah, yeah.
Yes. Yeah, okay. Interesting.
Okay, so as anticipated by the comments in the audience, there is a first law you can write for the inner horizon. This was first written down in the late 1970s by someone named Kerr. And the form of the solution that was originally written down had these minus signs. So you can absorb the minus signs into the t's and the omegas and the phi's that appear. And as we say, when t is negative, this just means the area of the inner horizon becomes smaller as you become more non-extremal. So is there nothing wrong with having a negative temperature in gravity? It's not as though it's a laser or anything like that. It's just a negative temperature. So that's fine.
So in statistical mechanics, we usually encounter negative temperature when the energy is bounded from above. However, in the case of black holes, is there any such phenomenon?
I think the way to think about this is properly in terms of a CFT description. So in the CFT description, for example, in BTZ, when I absorbed these signs, I have a first law for the outer and the inner horizons which look like this. The temperatures are defined in terms of the distances between the outer and the inner horizons. And the physical temperatures, I would say, are the CFT temperatures. The temperature of the left movers and the right movers. Those are always positive. So it's just the combination T plus minus in gravity that you obtain from these positive temperatures in field theory that can be of either sign. So at a level of the fundamental description in terms of the actual degrees of freedom, which you would associate with holographic description, I don't think there's any problem with negative temperature. I don't think there's anything to interpret really. But did you have something specific in mind?
So it's like, I mean, what you're saying, the density of states goes up and comes down.
Yeah.
So
Yeah.
I think
That's probably answers.
So here, in terms of BTZ, the area law, the independence of the mass on the right-hand side, it's just a consequence of level matching. So there's some momentum on some compact circle, which is quantized, and ensuring that is what makes the product of the areas here related to NR minus NL, which is independent of mass for the system. So you can write down the entropies of the outer and the inner horizons in terms of the temperatures and the central charges in the theory.
I'm really geometry between the inner and outer horizons is sort of time dependent.
Yes.
In a sense. The way the first law works, I think, for de Sitter black holes is that when you, or the second law rather, is that when you keep the area of the black hole horizon and the de Sitter horizon, that satisfies an inequality, right? Because
Yeah.
one can grow, but the other has to shrink, etc., etc. So this seems like here also you have two horizons in a time-dependent situation. And okay, I just thought I'd mention that.
Thanks. That's an interesting observation. I hadn't really thought about that, but that there might be something there. It'll turn out the region between the two horizons is really crucial, describing a lot of the aspects of the geometry. So that observation may in fact be an important one. Okay, so I'll just review something that people here know very well, the attractor mechanism. The idea is that n equals to supergravity in 4 dimensions. We find that if you start with scalar fields that have various values of infinity, they'll all flow to a particular value at the black hole horizon. And this mechanism for the flow is called the attractor mechanism. And it turns out the entropy is independent of the moduli at infinity. So this was described in the mid-90s by Ferrara, Kalish, and Strominger, and really explained about 10 years later by Sen. So the hand-waving explanation is that the number of microstates for a black hole is determined by quantized charges. And the moduli at infinity, they vary continuously. So as a result, the entropy of the horizon must be independent of the background moduli. And the moduli are fixed to values of the horizon that are determined by the charges consistent with the no-hair theorem. And we'll see how to make this precise as we continue. So you can ask whether the role of supersymmetry is what ensures the attractor mechanism works. And Sandeep and collaborators reply the answer is no. The attractor mechanism really relies on extremality, which is not the same as supersymmetry. So it's true for non-supersymmetric solutions, n equals 2 theory and n equals 0 theory and so on. It's just a fact that you need extremal solutions in order for this to work. So our goal is to apply these ideas to establish the curious properties we've noted for non-extremal black holes already. So the extremal case, we have some action written in terms of a bunch of scalar fields and a bunch of U1 charges. And from this action, we can write down the usual equations of motion. And we find that the ansatz which solves these equations of motion involves 2 functions, a of r and b of r in the metric. So the roots of a of r tell us where the horizons are, and b of r tells us the size of the horizons at those roots. And we have some ansatz for the field strengths, and the scalar fields are a function only of the radial coordinate. So the system can also be described in terms of some effective potential for the scalars. And this effective potential really describes the energy density of electromagnetic fields in the theory. And it turns out the minimum of this potential is what reproduces the area of the black hole in the extremal setting. So if you look at these equations, you can solve them. And the fact that there's a double horizon in the extremal setup means that certain terms here cancel. And you can regard the system as equations of motion corresponding to some one-dimensional theory with an energy constraint. So this is what Sandeep and Kevin and collaborators beautifully worked out many years ago. So it turns out then the conditions for an attractor are that there's the effective potential has a minimum, and the second derivative of the effective potential has non-negative eigenvalues. So when that's the case, it turns out the area of the horizon is described by the value of the effective potential evaluated on the attractor values of the scalar fields. So we've got some relation like this. And this applies, again, independent of supersymmetry. You only need extremality for the story to work. So what's happening is that if you look at these types of solutions, and you take the near horizon limit, there's an ADS2 factor. So this ADS2 is essentially an infinite throat. And whatever you do to the moduli at infinity, those fluctuations die off in this infinite throat. And that's why you have this attractor mechanism happening. The fact that there's this ADS2 is what kills off the fluctuations and ensures that you go to the attractor values at the horizon. So I just said that. Essentially, this infinitely long ADS throat is what accomplishes decoupling the degrees of freedom from the asymptotic boundary to the black hole. So we'll see there's a similar decoupling in spirit that applies to the region between the two horizons, which is also disconnected from asymptotic infinity. And we'll see certain features of the extremal solutions will translate into requirements on physics in the region between the horizons of a non-extremal black hole. So we can test the claims that we made numerically. So these are just some numerical solutions with a bunch of different scalar values of infinity, and we flow them to the attractor values at the horizon. So let me take a brief aside and mention some comments on how to interpret this radial evolution in terms of the C theorem. So this is some work that I did some years ago with Arpam Bhattacharya, Shubhajit Haq, Suresh, and Alvaro Veliz-Osorio. So the idea is that there is a C theorem, and for a unitary CFT, there's some positive real function such that it's monotonically decreasing along the flow. It's stationary at the fixed points. As at fixed points, when you evaluate at the UV and the IR, you get the central charges of different CFTs. So the C function will satisfy some Kalan-Zemansky equation and it counts degrees of freedom, which we associate to the central charges at the fixed points. So this work in 2 dimensions was done by Zimolodchikov, and it was generalized to 4 dimensions by Carty and proven rigorously not so long ago by Komargatsky and Schwimmer. What they showed was that the C function in 4-dimensional theory is really the A coefficient of the Euler density, which appears in the expectation value of the stress tensor. So here, we're not going to look at the general C theorems people have studied that go from vacuum to vacuum. We'll look at some non-vacuum to non-vacuum C functions that we'll use the attractor mechanism to construct. So I'm thinking of a black hole in ADS space, and I have some ADS-D boundary corresponding to CFT d-1 with a central charge I associate as CFT. The near horizon can have a different ADS2 factor in its geometry, and there's a different CFT that's associated to this boundary. They both count the entry of the black hole, of course. So you can think about some flow from a CFT here to a CFT there. So what are the properties of this flow? Well, the degrees of freedom, which are counted by the C function, need to decrease along the flow, and because renormalization integrates out degrees of freedom as you proceed along a flow. We know the scalar fields in the infrared are fixed to some attractor values for an extremal black hole, and we know the flows we've seen for particular values in moduli, we know they're a monotonic. So we'll use this to construct a C function for these black holes embedded in ADS space. Yeah.
Can I say something in this picture of the UV CFT flowing down to the IR CFT?
Yes.
So suppose I compute some correlation functions in the microscopic
Yeah.
field, and then I start taking the low energy limit of that and ask what are they reproduced by? I mean, is it reproduced by some thing which reflects this conformal symmetry of ADS2 or something? So I thought some of the exponents which you get depend on the angular momentum. You see what I mean? These are.
So I think.
What is the? Isn't that right?
So. Yeah.
Yeah.
That's correct.
That's right. Yeah.
That's correct.
So I think you're probably describing some. So the way I want to think about this is that there's some ensemble of states in the UV CFT, which describes the black hole. And there's some ensemble of states in the IR CFT that also describes the black hole. In principle, you can just count the entropy either in the UV CFT or in the IR CFT. You should get the same answer because it's the same black hole you're describing. Maybe you're counting entropy density as you're approaching the near horizon, but roughly speaking, you should be able to integrate over that, say, the angle, and recover the entropy of the black hole. It's
So
not
I
clear.
Think of a different CFT associated with ADS2 for a different angular momentum.
Yes.
No, one shouldn't think of it that way.
I think.
Even though the exponents do depend on
Yeah.
Okay, those are just different modes in ADS2. You know, if you think from the ADS2 point of view,
I see.
you get the different KK modes on the S2 are different massive fields. And so the dual operator is
I see.
So from the CFT point of view, that would be the global symmetry, additional global symmetry.
Right.
And such a flows also exist in higher dimensions. So
Yeah.
You only have an empire being.
What's unclear is how to understand which states get mapped to which states. Presumably, that can be understood. Maybe using supersymmetry. If you have short multiplets, maybe you can match short multiplets in the asymptotic theory to short multiplets somehow in the infrared theory, and see whether you can see how the states get mapped, maybe in special examples. As far as I know, that really hasn't been done. It's also, if you have some ADS5 going to some ADS2 or ADS3 near horizon, you start off with SOD, 2 as your conformal group. And in the infrared, you're getting some 0, across 0. So you're going from some finite dimensional group to some infinite dimensional group. So somehow the generators are reorganizing themselves along the flow in order to give you this, this higher symmetry algebra. It's not clear how that happens, although it has to.
But that higher dimensional algebra is only an effective sort of symmetry at low enough angles
Yes.
in the flow.
Yeah.
But you're right, yeah.
In a sense, you're also mixing maybe the R symmetry with the conformal algebra in order to get the symmetries in the infrared. So it could be a hard problem to disentangle how these pieces fit together. So,
I can make a
yeah.
comment which is somewhat apart from this discussion, but it's related to this flow across dimensions. As I said, you can think of empire flow from the 6D theory, living on the empire plane, compactify flow with dimension flow to 4-dimensional CFT. And there is some understanding of how, let's say, the index of the empire plane that you compute in the 6 dimensions, which reproduces the index of the 4D. So there you have to look at the compactified manifold and use Riemann Roch theorem to look at which states survive the supersymmetry.
So in gravity, a proposal that Sandeep and collaborators made was that if you look at the area of shells, radial shells, as you go towards the asymptotic boundary, this can be some C function, which will eventually at the infrared recover the physics of the IR. This suggestion has the difficulty as you go to infinity, these shells are becoming larger and larger in area. So in a sense, you need to figure out how to regulate the flow in order to construct some finite C at infinity if you're going to use these radial charges, these radial slices. So what we propose is just using the fact that the attractor mechanism can describe the derivative of the scalar field in the radial direction in terms of some generalized superpotential and n equals to supergravity. And we can just consider some function like this. And we can use the values of the central charges in the UV and the IR to fix the coefficients that appear. So we do this, in fact, for example, interpolating between ADS5 and ADS3. The attractor equations give us this form of this term in this expression. And if you take the total derivative of this whole term, you recover something which by the null energy condition has to be positive. And as a result, the derivative of C is such that it vanishes only at the endpoints by tuning these coefficients appropriately, and it strictly decreases as we go to the interior of the spacetime. So this is some function, some real function, only in the scalar fields that respects some vector transformations on the moduli space of scalars and interpolates between central charges in the UV and the IR. And it's basically extrapolating between solutions which are non-vacuum on both in both the CFTs.
What does C of R mean?
It somehow will count degrees of freedom along the flow the same way any C function would.
How do you
Become
com-
R
how do
like
you
a
compute?
scale.
Yeah, but how
Yeah.
do I compute C function in a theory that is not conformal, somewhere in between R as a one-bit theory question?
I don't know. I don't have a sharp explanation. There is just, however, you can interpret this at the UV point and the IR point as a normal central charge. And there's a family of, it's not unique, there's a family of monotonic functions that interpolate between these two. And they have a natural geometric interpretation in terms of the scalar fields in the bulk. That's all I can tell you.
Beta function
Okay, so that was an aside. Let me go back to the main theme. And in prior work with Kevin and Suresh, we described certain features of the extremal and non-extremal solutions, which we'll attack in the more general case. So I'll just state the results we had initially. We noticed the attractor equations, by virtue of the factors in ADS2, ensure that the quantities in angled brackets here directly vanish. If you take these same quantities which vanish in the extremal case and you integrate them over the region between the two horizons, they continue to vanish. So in a sense, the attractors equations for the extremal setting apply to the non-extremal setting in some average sense. The measure for this averaging is just dr. So a priori, it's not clear why there shouldn't be some measure factor that appears additionally. But if you just happen to do these integrals over the region between the horizons, these quantities still vanish. Okay, so in the new work, we'll extend these ideas to higher dimensions or infinite dimensions, and we'll look at gauged supergravity as well as the ungauged case that we've been studying. And we'll also look at complex horizons. I don't know what the geometric or entropic meaning of these complex horizons will be, but we'll see that they're crucial to determining certain invariants in these geometries. And I'll say a few words about rotating black holes and interpreting the entropy of the inner horizon region. And I'll construct some new invariants for these non-extremal black holes. Okay, so the system is essentially the same system as before. We just add a potential here for the scalar field, which appears essentially like a cosmological term. This is generated from F5 parameters in n equals 2 theory. And the ansatz is very similar to the ansatz that we had previously. We just generalized this to d dimensions and write down the equations of motion. So these equations of motion look tough, but if you do a clever change of variables, you'll find the prior equations look rather similar in form to the equations we saw in the 4-dimensional case. And these system of equations can be solved so far in 2 different cases. One is we set this extra potential to 0, so we're back in the ungauged case. And the second is when we set the scalars to constant values corresponding to the attractor values. And we have a non-zero potential that appears as a cosmological term. So in general, the scalars will assume values of the 2 horizons that depend upon the moduli of infinity. So if you look at the analog plot from before, the blue dots correspond to the outer horizon, the red dots correspond to the inner horizon. You find that they have different values based on the asymptotic moduli you have. In some cases, the attractor value is the average of the values at the 2 horizons. In other cases, the horizons, the attractor values, you find twice in the inner horizon region, and the values of the 2 horizons are the same. So these are cases we looked at numerically. We could. So the value of the scalar field of the extremal black hole in this case is the average of the values of the 2 horizons. So the extremal black hole value is the thing in the middle. And in this family of solutions we looked at, if you consider case 3, for example, the flow will intersect the attractor value 3 times and so on. So there are a bunch of different possibilities that could happen. There's no, if you look, however, at the effective potential, you'll find that in many of the cases we looked at, the effective potential evaluated on the 2 horizons is the same, and the minimum happens somewhere in between multiple times. The minimum corresponds to the attractor value for the scalars. Okay, so the ungauged case in g dimensions, what? The horizon is, the outer horizon is the blue dots, the inner horizon is the red dots. So in the ungauged case, it's rather similar to what we looked at previously, and we find that the effective potential evaluated on the attractor values is related to this new row coordinate introduced at the outer and the inner horizons, which is related to the row coordinate for the extremal solution. And this is the analog of the area law in higher dimensions. And as well, if you integrate the attractor equations over the region between the 2 horizons, you'll find that this also equals 0, just like in the 4-dimensional case. So if you derive the geometric mean, you can sort of argue this as follows. I'll make the argument for the purposes of the talk where entropy is proportional to area. We can generalize this to situations in which entropy and area needn't be proportional. So this is really something which you can say about the area rather than the entropy. But in the simple case where these are related, we find that there's a relation between the area of the outer horizon times the temperature of the outer horizon and the area of the inner horizon times the temperature of the inner horizon. And this is related to the non-extremality parameter, which essentially describes the distances between the two horizons. So in this setting, this expression here, because S is proportional to the area, S plus T plus plus S minus T minus is equal to 0. If we take the mass derivative of the product S plus S minus, you get this expression in the numerator. So we have this derivative vanishing. In the delta goes to 0 limit, S plus equals S minus, and as a result we conclude that this invariant is S extremal squared. So this is sort of a thermodynamic derivation if you accept some meaning to the first law at the inner horizon. We can also look at the wave equation in these backgrounds. And we find that if you look at the wave equation, you perturb the moduli away from the attractor values, you have some equation which you can express as a Klein-Gordon equation for static scalar fluctuations of a mass in some ADS2 background. So essentially you're doing some rescaling of the metric in order to get this ADS2. And once you do this rescaling, you'll find the mass in ADS for the scalar is really the mass that we started out with, this mass deformation we started out with, divided by a non-extremality parameter. So the limit when the non-extremality parameter goes to 0, we develop an infinite mass gap, which explains why fluctuations die off in the extremal case. So a CFT interpretation, an idea due to Svedich and Larson and Svedich and Gibbons, is the notion of subtractive geometries. So what you do is by choosing warp factors judiciously, you can take a black hole in asymptotically flat space and translate it to a black hole in asymptotically ADS space with the same thermodynamic properties. It's a different black hole, of course, but the thermodynamic properties remain the same. So by judicious choice of rescaling of things in our metric, we can convert a flat space black hole that we've been studying to a black hole with asymptopia ADS2 cross SD minus 2. This so-called Harrison transformation. This works in the case of constant scalars. We haven't been able to do this for non-constant scalars. We fix the scalars to their attractor values, and we employ this Harrison transformation trick to translate our black hole into a different black hole with the same thermodynamic properties in different asymptopia. Now, in this
Math is like, it's like a redefinition of the metric, or I'm a bit confused about
so
much about this math. Like,
you just take some black hole,
some back.
and there's certain warp factors that appear in that metric for that black hole. You find some transformation of those warp factors,
I see.
and that converts it to a black hole with the same thermodynamic properties in a different asymptotic setting.
I see.
So it's a different black hole totally. However,
Even on those can be there.
What?
From EDS you can go to flat space.
yes, Yeah.
But doesn't the thermodynamic properties depend on the theory?
But changing the warp factor, we have changed the theory.
yeah,
This is without any reference to the theory, just from
Right.
the solutions.
So if we do this transformation for the Bryson-Nordstrom with constant scalars, and we use a graviphoton to do a collusive-Klein uplift from ADS2 to ADS3, we get a BTZ black hole with the same thermodynamic properties. And we find the mass of this BTZ black hole is proportional to L0 plus L0 bar, and the angular momentum is proportional to L0 minus L0 bar, which is proportional to product rho plus rho minus. So these are orthogonal directions. So you can change the mass while leaving J fixed. And J comprises rho extremal squared. So this sort of explains how the orthogonal eigenvalue remains constant while you change the mass parameter. And this applies not to the original black hole we looked at, but to this related black hole by Harrison transformation. So it's suggestive, but it's not a proof of anything. But it suggests there may be some CFT interpretation we can associate to the original black hole. And that's somewhat corroborated by the appearance of an ADS2 factor in the study of the scalar fields in this background. If you look at the infinite dimensional theory, we'll find the gravitational potential will go like 1 over r to the d minus 3. So the d goes to infinity limit, the gravitational effects localize the length scales, which are suppressed by 1 over d. This is something that Emperon and collaborators looked at, and also Shiraz and collaborators here. So if you apply these ideas to extremal solutions in infinite dimensions, you find the flow essentially becomes a step function. So the moduli retain their asymptotic values until a region very close to the horizon, and then quickly drop to the attractor value. And we do this numerically for various values of dimensions up to 10. Okay, so we looked at ungauged supergravity so far. Now we'll look at gauged supergravity. In gauged supergravity, will require for our solutions to make sense that the effective potential and the gauge potential, these both need to vanish. So generically, there are 2 n equations and n variables, but typically different scalars appear on these 2 different potentials, so you can in fact minimize both of them. And the simplest solutions have been found. They constitute constant scalars fixed to the attractor values. And demanding that the metric be time-like at large radial distance requires us to be having a minimum for this potential to be negative. So this corresponds to ADS-like solutions. And these first solutions with these constant scalars were written down by Toldo and Van Doren. And they didn't note the following, but they could have in their paper. So I'll give them credit for it anyway. If you take the product of the complex roots to a squared b squared, corresponding to where the horizons would sit if you complexify their positions, that product, r plus r minus times lambda modulus squared, is not the same as r extremal to the 4th. So for these solutions, it's not true the extremal area is the geometric mean of the areas of the non-extremal horizons. However, it does turn out that there are invariants that correspond to the products of all of these roots. Okay? So what are these horizon invariants and how do we derive them? The horizons are determined by a squared equals 0. And in general, there are n complex roots. In the 2 horizon case, I'll go over what happens. I'll generalize the story to the multiple horizon case. So in the 2 horizon case, we have this effective potential, which we were told to extremize. And we know at the horizons, a squared vanishes, and also delta a squared vanishes. So with this constraint, we can write down this relation. And noting that we define a squared prime b squared to be the distance between the horizons, the non-extremality parameter, which we'll call alpha here. We can write this expression in terms of alpha L minus and alpha L plus with a constraint L plus minus L minus equals 1. And we can show that this is true. Now L plus and L minus, these parameters we introduced, on the space of solutions, the ratio is constant. So from this, we can use what we know to express this guy as that guy over there, and this expression here, the thing whose delta vanishes, that's some function just of the charges. And by going to the Rise-Nordstrom point as a reference, we can fix this expression to be r plus and r minus is r extremal squared, and we conclude then that L plus equals minus L minus, and the product of the areas is just a function of the charges for this. So this is a derivation of the area law for the non-extremal case. Now, if you look at more complicated settings where there are multiple roots in gauge supergravity, you'll find the roots are sitting somewhere on the complex plane, and their positions are just given by solutions to a squared equals 0. And an analytical argument will show the product of the areas that sit at these different roots in the complex plane is going to be some ratio of the minimum of the effective potential and the minimum of the gauge potential. So this is an invariant for this system. And it requires, crucially, that we take the existence of these complex roots seriously. We can also do something similar for stationary solutions. So for stationary solutions, instead of looking at inner and outer horizons, we just look at Killing horizons. And Wald and Iyer developed this technology to show that there is some S you can associate to each Killing horizon. You interpret S as the Wald entropy for the Schwarzschild solution, but in general, it's just some Noether charge associated to the Killing symmetries. And it turns out the product of these Killing charges associated to these horizons, that's also an invariant for these stationary solutions. But the entropic meaning of this, I can't tell you. So what can I tell you about entropy? Not very much, but I'll give it a go. So we can write the first law for any of the horizons we've encountered, including the complex horizons and these Killing horizons. The inner horizons are unstable, so it's not clear whether we should think about these first laws as really describing that of an entropy. In particular, the inner horizon can't see the asymptotic vacuum, so it's not clear how this would be an entropy. But let's push forward. And we don't know what the area of a complex horizon even means. But we have a setting in which the entropy of the black hole is given by the area of the event horizon. And if we think about the inner horizon as being an entropy, it will count some subset of these degrees of freedom. So S minus is x extremal squared divided by S plus. As I said, there's a possible fuzzball interpretation that Martinek proposed, but it's not clear what the extremal limit of this would be. So I'm not going to push this idea too hard. But we know that region 2, which is decoupled from the asymptotic of infinity, is crucial. It gives us the average attractor equations. So for Sandeep's benefit, he stepped out. These are the attractor equations. And if you integrate the attractor equations over the region between the two horizons, they still vanish. So this is a property of these non-extremal black holes that we found. So they hold in an average sense. And this applies in the region between the two horizons. So if you look at BTZ and we compute the difference between S plus and S minus, perhaps that's accounting for perhaps the degrees of freedom of the outer horizon capture what's inside the black hole. Degrees of freedom of the inner horizon capture what's inside the inner horizon of the black hole. So the difference would then capture whatever is in region 2, very naively. So if you look at what this difference is in terms of the CFT description of BTZ, it turns out it's only related to the left moving sector. So in a sense, if you have an extremal black hole, you excite one side, the right movers. And if you have a non-extremal black hole, you excite the left movers as well. And maybe the left movers then, they're giving you two horizons. Somehow their degrees of freedom, if you interpret this as the difference between S plus and S minus, their degrees of freedom are then isolated in region 2. Now, this is maybe a dubious proposition because regions 2 and 3 really aren't independent in that you're forced to move radially in region 2 towards region 3. And also, we know there's entanglement across the horizons, so it's not like the Hilbert spaces will factorize in a neat, nice way. So this interpretation may be an approximate sort of interpretation. But it's sort of interesting. The difference between S plus and S minus corresponds to the set of oscillators you turned on in order to generate a non-extremal solution.
But there is entanglement on the left and right.
There is entanglement on left and right, yeah.
Left moving sector and the right moving sector. So why do you say this is not quite, doesn't quite fit in this, at least the entanglement part?
So you would think that degrees of freedom in region 2 are, you can maybe think of a bell pair in region 2 passing into region 3. There's entanglement across the inner horizon. If you're interpreting C2, if you're interpreting the left movers, the CFT, as describing only region 2, it's not clear to me how you...
Well, in CFT also, the left and right
yeah.
movers would be entangled.
Yes. So what I'm saying is sort of approximate is the idea that region 2 is only described by left movers.
Yeah.
I agree with you then. So
Entropy is suggestive.
it's suggestive. I don't know. So as well, in order to determine the temperatures, we did Euclidean continuation. So computing the temperature in region 1 is just a standard thing to get the cigar. And similarly, we can compute Euclidean continuation in region 3 in order to get the t minus 1 inverse, maybe the absolute value of t minus 1 inverse by doing the Euclidean continuation there. We also notice, as usual, that the Euclidean path integral gives us some description of the entropy in terms of the free energies of the partition function. So we've noticed that complex horizons contribute to invariance. What do they mean in terms of this kind of story? I don't have an answer, but I think it's a good question to explore to figure out the meaning of the complex horizons maybe by studying this kind of thing. In solving for the area law for these extended non-extremal solutions in higher dimensions, we ended up essentially using VHS formula in order to find the product of the roots of a certain equation. So VHS formula will tell us the ratio of C2 to the coefficient here is what tells us the product of the roots is this guy that we use to determine the invariant. But there are a bunch of invariants here from this formula. You can take the ratios of any of these coefficients in order to construct invariants. And it's not clear what these mean either. It's also not clear what happens when the scalars are non-constant, as the only case in gauge supergravity we're able to study is the case of constant scalars. Okay, so let me summarize. We use the attractor mechanism, and we show that the attractor mechanism, which fixes moduli at the horizon, can be used to motivate invariants for non-extremal solutions. And we notice the product of the roots is one such invariant, and the attractor equations are averaged over the inner horizon region. We produce, they vanish in an average sense. And we notice that there are new invariants we can associate even to stationary geometries. In ungauged supergravity, we notice the geometric mean of the area of the inner and the outer horizons gives the extremal area, but in gauged supergravity this is not necessarily true. There is an invariant, but the geometric mean formula no longer applies. In infinite dimensions, we notice the evolution of the moduli essentially follows a step function. And we looked at this in a number of settings. Open questions. We've noticed there's quite a bit we can say without using supersymmetry and extremality, but we've noticed that everything we've said so far is really only thermodynamically oriented. We really don't know very much about microstates in non-extremal geometries. There are fuzzball microstates, but there are not anywhere near enough fuzzball microstates to account for the entropy. It may be that such states don't exist in general because of the scaling arguments by Sen that there are states that you just can't describe in gravity, which are microstates for these systems. We have some open questions regarding how to interpret the various entropies we associate to these various horizons. We don't know what the Euclidean continuation means inside the black hole, and we don't know what these new invariants mean. We can look at higher derivative corrections, logarithmic corrections to entropy, and see what happens there. We can also connect to various new proposals for near-extremal physics. So you had a paper this summer, and Finn had a paper recently as well. I haven't really tried to connect these ideas to the work in your papers, but that's something for us to look at as well. So that's all I have. Thank you.
In the last point, the geometries were essentially extreme, right?
Which geometries?
When you refer to Sandeep's and Finn's paper.
Yeah.
And then look at the departure as
But this was for near.
From the outside, yeah, where you study the response, right? Mm-hmm.
This is for near-extremal systems, right? Here, this can be very non-extremal, and you would still be able to use the attractor mechanism to say these things. So it seems this setting that you guys developed many years ago is a very powerful technique for at least understanding certain aspects of black hole geometries. So maybe the attractor mechanism can be exploited further, even in a non-near-extremal setting.
Could be. I mean, we mostly looked at the region outside the outer horizon and the responses seen from the outside and how that can be described through fluctuations of the boundary of the near radius 2 region. But it's interesting from the inside. I mean, in the stepped out, but just briefly, so this geometric formula doesn't work in gauge supergravity, but you have some other invariants.
So yeah, what happens is, so if you look at constant scalars, which is the only solution we have in gauge supergravity, if you just compute,
Constant, you mean the asymptotic values?
the asymptotic value is the attractor value.
Okay.
So you look at that setting, and you find that the product of the roots is an invariant. This invariant turns out to be some ratio of the minimum of the effective potential and the minimum of the gauge potential. However, if you look at this product and compare it to the extremal result, this is not the geometric mean of this product. But this is still an invariant.
So it's, as you said, there are other invariants in the story.
You had this big, I mean, you briefly mentioned this proposal from the CFD side that the middle should make a that
Yeah.
move us. So, if there are multiple horizons, how would you?
I don't know. This was just for PTZ. I don't know what happens. You know, if you take the, there are going to be two real there's going to be two real roots to this expression. If you take those two real roots, you'll still find that if you integrate these expressions between those two real roots along the real line, that will vanish. So the attractor equations, you know, this integral applies, even if there are multiple roots. But I don't know how the BTC story will generalize.
So B was what again?
D is dimension.
B.
B is the area. So the metric ansatz was it's two-sphere radius, yeah. So
Function of radius?
it's a function of radius, yes. So where is it? The ansatz is here.
Okay.
Yeah.
Comment about this linear continuation of the
Yeah.
interior region. I guess you're saying it's kind of a time-dependent geometry. So what does it really
Yeah.
mean? Now, you know, sometimes these geometries can be embedded in, that kind of Schwarzschild black hole can be embedded in six-dimensional space. You know, just like I think there is a way of writing the Schwarzschild black hole as a surface in a six-dimensional place. It's very old work by Dazer and company. You know, pretty much like, you know, ADS spaces are
Yeah.
surfaces in this thing. So in the embedding place there is an equation. Sometimes it's possible to continue that equation in,
I see.
in an
Okay.
unambiguous way. You know, like the same thing happens with de Sitter. If you use like, you know, steady state coordinates, then it's a bit troublesome how to continue de Sitter to sphere, right? But on the embedding space it's quite clear. So maybe that
Okay.
gives some sense of definition. I don't know whether these black holes can also be thought of surfaces in six dimensions.
How does this embedding space function?
I forgot. It's a very old paper by Stanley Dazer and somebody.
Okay, I didn't know this paper.
All I remember about this is it's not one more dimension, it will go two more dimensions for some reason. So it's a radius surface.
In conformal field theory also you use embedding space with two.
That's also true, right? But that's got to do with the comma two thing, right? I mean, conformal field theory that depend that is right. But all I'm saying there could
Yeah.
be an unambiguous way of
And you think this might apply to complex horizons as well?
I don't know.
This, we can continue this later, but this, no, I had studied a little bit, but now I've somewhat forgotten the story you mentioned of Eric Poisson and so on, of mass inflation in the
Yeah.
linear horizon. Now, I think they tried to take into account the back reaction, is that?
They tried, but I don't think they did anything beyond linearized
Yeah.
perturbation theory.
But I've always been curious in the context of a S-wave reduced 2D model, you know, where the quantum back reaction, the matter is whether we can make that story precise. Because the in-between region, again, to come back to this, is really like a cosmology, you know.
Yes.
And if we can make that connection a little more precise, then the fact that you get these interesting thermodynamic relations, etc., I mean, that might become something really interesting. So anyway, yeah. But yeah, it was more a suggestion. I mean, they couldn't do a definitive calculation.
Yeah.